Welcome to the next class. That is, we are going to see about the torsional pendulum. The torsional pendulum you can see in the figure. So the torsional pendulum means the one end it was fixed one, the another end which is free that was connected with the disc. Which disc means it is a metallic disc, circular in shape. So in its center part, it was connected with one steel wire, any or metal wire, steel or anything metal wire. It was hanged. This is called as a torsional pendulum. This torsional pendulum, we have to drag it. Drag it means we have to give a twist. In a normal simple pendulum, which was connected with the normal thread or anything, and the end was connected with the ball or bob. This was dragged means it is going to here and there. That is to and fro motion will be produced. That is a simple harmonic oscillation will be produced. So there will be a change in length. But here we cannot drag it because it is a circular metallic disc. So we have to produce a twist only. So the twist may be in a clockwise motion or in a anti-clockwise motion. What happens? It from the twist we are keep our finger in a one finger in one side and another finger on one side. So it have to produce a twist. So the two fingers gives a couple. That is, couple means two equal and opposite forces acting on a body. So we are giving a couple, so it produces a twist. This twist produces an oscillation, that is, it is going that side and coming the side, that is, it going clockwise, and restoring couple produces the anti-clock. Otherwise, the force was applied in a anti-clockwise, the restoring couple will gives in a clockwise direction. So twist will be produced. So there will be a to and fro motion here and there. This oscillation is called as a torsional oscillation. So here we are going to connect about the rigidity modulus of a torsional pendulum. So what do you mean by rigidity modulus? The torsion involves a shearing strain and hence the modulus involved is the rigidity modulus. Here the complete weight of the metallic disc was bared by the steel wire. So whenever we have produced a twist, every stress and strain will be appeared on the wire only. The wire will go under the modulus. So this modulus is called as a rigidity modulus. We are going to derive the rigidity modulus in the torsional pendulum. So what principle is applied here? When a disc is rotated in a horizontal plane, the disc executes simple harmonic oscillation due to the restoring couple produced in the wire. So what's the pendulum? The one end it was fixed to a split chuck and the other end fixed to the center of the circular disc of radius r. Let L be the distance between the chuck end to the disc and r be the radius of the suspended wire. The circular disc is now rotated in a horizontal plane so that the wire is twisted through an angle theta. The various element of the wire will undergo shearing strain and a restoring couple is produced. Now, if the disc is released, the disc will produce torsional oscillation. The couple acting on the disc produces an angular acceleration in it, which is proportional to the angular displacement and is always directed towards its mean position. So, from the law of conservation of energy, we can write the total energy of the torsional pendulum will be equal to potential energy plus kinetic energy. The potential energy confined to any of the body can be done in twisting the disc, thereby creating a restoring couple. Restoring couple through an angle theta, that is a displacement we are given by the twist, that is theta, will be equal to integral 0 to theta moment of couple into d theta. That is, finally we will get c theta square by 2. P potential energy is due to the restoring couple given by an wire, not by us. We are giving a twist that is nothing but couple, that is called as a deflecting couple. We are given a deflection. So this is due to the kinetic energy. We are giving a kinetic energy, the wire giving a restoring couple. Wire giving a potential energy. Okay. So come to the kinetic energy. Already we have derived this kinetic energy in my one of the previous video, that is the half high omega square is nothing but rotational kinetic energy. Next, coming to the total energy. So the kinetic energy is equal to half I omega square. Then coming to the total energy, P will be is equal to potential energy plus kinetic energy, that is C theta square by 2 plus I omega square by 2 will be a constant, because we told the conservation of angular momentum. So the if it is a conservation, we have to give it as a constant. So then differentiating equation with respect to time. Here the both in equation 4, both theta and omega is a variable. So we have to differentiate omega with respect to time and also theta with respect to time. Then see theta, the theta, that is the theta square, while differentiating, it will become as a 2 theta into d theta by dt. The 2 and already having there 1 2, that will be cancelled. So finally we will get c theta, and once again we have to differentiate the theta, so we will get d theta by dt. As the same, we are going to differentiate I omega square by 2. Here I is a constant. Omega square, while differentiating, it will become as a 2 omega into d omega by dt. Already 1 2 is there, so both are cancelled. So finally we will get I omega into d omega by dt. Here this equation have to be changed completely with theta or completely with omega. So now we have to change this with completely theta. So we have to replace the omega in terms of theta. So coming to the omega, already we know that is the angular velocity, that is d theta by dt. And according to the displacement theta, we have to write the angular acceleration is equal to d square theta by dt square. Next, substitute this value there, then we will get c theta d theta by dt plus I d theta by dt into d square theta by dt square is equal to 0, because in total energy we wrote a constant. The constant after differentiation, it will be become as a 0. That's why we put a 0 here. Then in this term, who's common? D theta by dt is common. So d theta by dt, the remaining thing is c theta plus I d square theta by dt square is equal to 0. Here the d theta by dt will not become as a 0. So the remaining, this bracket term will become as a 0. Bring this term, we need d square theta by dt square is nothing but angular acceleration is equal to minus c theta by I. So we got angular acceleration. This negative sign indicates the couple tends to decrease the twist on the wire. So in the that is the so after each and every oscillation, it the twisting displacement will be decreases. So finally, after some oscillation, the pendulum will becomes a rest position. Then for any of the oscillation, we have to calculate the time period and frequency. Already we know the time period formula, that is 2 pi into root of displacement by acceleration. Displacement here is nothing but theta, but acceleration now only we calculated, that is nothing but angular acceleration c theta by I. The minus is negotiable here. The time period of torsional oscillation t is equal to 2 pi into root of I by c. Then frequency, that is nothing but 1 by t. So whatever t, take a reverse, 1 by 2 pi into root of c by I. Next, so now only we are coming to a point, that is we have to calculate the rigidity modulus of the wire. We know the torque per unit twist per couple, the value is n pi r power 4 by 2l. This was already derived in some other topic. So we have to substitute the C value in the time period formula. The time period formula C is equal to pi into root of C by I. So here we have a C value, that is n pi r power 4 divided by 2L. Then we will get a, which one we need? We need a n value, that is nothing but rigidity modulus. So to take a rigidity n value, it was in root. So we have to remove the root. So take the square root on both sides, squaring on both sides. That is t square is equal to 4 pi square 2li divided by pi n r power 4. So after solving, we will get the rigidity modulus n is equal to 8 pi I L divided by t square into r power 4. So I think you understand how to calculate the rigidity modulus for the torsional pendulum. Thank you.